I'm delighted that next up we have Vish giving us a lecture on PyTorch. So PyTorch, as many of you know, is an open source machine learning framework based on the Torch library, which is widely used in the deep learning community and especially in the deep learning research community. So excited to hear this talk and lecture. Vish, take it away.
Sure. So let me share my screen. Okay, so as mentioned, my name is Vish Rao. I'm a member of the Harvard Medical AI Lab, and I'm excited to present to all of you NLP with PyTorch. So the premise of this presentation will be both an introduction to the basic task of NLP, as well as how to use PyTorch in order to do so. So as mentioned, there are three key learning goals that we have for this lecture. So firstly, we want you to understand the basic NLP tasks and applications. So we're going to delve deeper into specifically clinical text classification. So that will be the specific task that we deal with. But then we also want you to gain exposure to some of the common data pre-processing and formatting techniques required for the implementation of NLP algorithms. So in this case, this will include vectorizing your input string. And then finally, we're going to go through how to actually apply PyTorch as a deep learning framework for the data loading, training, and logging. So with this in mind, let's start with a motivational example to get an idea of why we want to do this in the first place. So this was a study that was recently conducted in order to basically classify cancer diagnosis based on a patient's electronic medical record. So the reason why this is important is because currently diagnoses at least for the medical record are based on billing criteria, which is not the most accurate, especially when dealing with more common conditions. So there's a lot of mix-ups in that case. So basically what this study did is that they had this set of medical records that were anonymized, and they pre-processed them, they vectorized them, and then they're creating embeddings for them. And then they dealt with multiple different tasks. So some of the tasks were, for example, breast cancer versus other types of cancer, cancer versus non-cancer, many different tests that they did. So they tested deep learning versus traditional machine learning algorithms in order to ascertain which approach is actually better for this kind of task. And then they extracted the results using common classification metrics such as F1 score, precision, and recall. And then they compared the results. So this is a sort of typical NLP framework that someone can take for approaching clinical data classification. So this isn't really that important, but this is just an example of some of the results they achieved. And we can see that across the board, their F1 scores were very high with close to a value of 1. So they compared both across where the x-axis here is different disease diagnosis tasks, whereas the colors refer to different types of embeddings. So basically, they were able to find that the performance varies by task and by embedding, which was very useful to know. So based on this, let's go ahead and get into the actual agenda. So first, we're going to go through a basic introduction to PyTorch. So this is going to be why PyTorch and some of the basic mechanics for this framework. And then we're going to get into coding. So I will be live coding some parts, so expect some mistakes, just common with coding. But anyway, yeah, so we're going to start with dataset exploration. So we're going to be loading our initial data frame, building a vocabulary, which you'll see is quite imperative to actually converting your words into numbers. And then we're going to build a data loader using PyTorch, and also going over how to incorporate your proper pre-processing techniques within such a data loader. And then we're going to sprint into train validation, which is common in machine learning applications. And then we're actually going to be defining our model and training. So this will be especially pertinent in PyTorch because we'll set up a training loop and then go through terminal logging and also GPU training. So let's start with an introduction to PyTorch. So before actually getting into the conventions of PyTorch itself, let's quickly touch on why we want to use PyTorch in the first place. So the key advantage of PyTorch is automatic differentiation. So basically, you can think of this simplified case as follows. So we have some model which has a certain number of steps in it that takes in these parameters and then has this output y. So we can see that PyTorch basically builds a computational graph for the model that allows it to track gradients at every single step. Or we can see that these are the edges of the graph that PyTorch is able to track the gradients across. So we can imagine that if we have our loss, we can actually trace back the gradients to each of our parameters and find the gradient with respect to each individual parameter. And this is useful as, for optimization and backpropagation, we need to know the gradients with respect to each parameter in order to update them accordingly. So this is why we use PyTorch compared to other frameworks such as NumPy. And PyTorch also has other advantages such as GPU training, which we'll get into. So with this said, let's go over some of the most common practical tools with PyTorch. And perhaps the most important is the use of tensors. So tensors are very similar to NumPy arrays, and they actually have the same format, and you can use many of the same NumPy operations using tensors. So you can convert to and from NumPy. And the key advantage to tensors is that you can actually transfer these tensors to a GPU in order to accelerate training. So here is some basic syntax for defining a tensor and transferring it to a GPU. So we can see that we have this data, which is simply an array, and then all we need to do is call torch.tensor on the data, and then we convert that into a tensor. So then, just like that, we can also easily transfer this tensor to the GPU, where we first check whether the GPU is available, and then if so, we transfer it there. So here are some other important components. So we're actually going to go more in depth into each of these as we go through the coding instructions, but this is still good to go over in the first place. So we have the dataset class. So the dataset, first of all, the purpose of a data loader in PyTorch is to basically give us batches of our training samples and our labels as we're looping through our training loop. So this data loader basically packages them all together and makes it easy for us to iterate through them. So the dataset consists of 3 key components. So along with other helper functions. So you have the initialization, which is the same as other classes in Python. Then you have the length function, which basically tells you the length of the dataset that you're dealing with. And this is important because when you're iterating over your entire dataset, you need to know the length of it. So what index to start and what index to end. So that's why that is critical. And then perhaps the most important is the get item function, which will basically where you go through the set of input procedures in order to return the input to your model and its corresponding label. So using this dataset class, you can pass it into PyTorch's data loader, which is a class within PyTorch where you can declare as follows, and that is what you actually iterate over. And then so this is an example of like a very bare bones example of how you could iterate through and train a model using this data loader. So we would iterate through the data loader, and then we would find the output by just calling model on the input. And then we would find the loss by using the criterion, which you would have defined earlier, finding the loss there. Then you would reset the gradients on the optimizer, backpropagate, and then update your model. And then I have this line here that's saying basically save the model parameters. And this is useful when you're training. So say we want to save our model when we hit, for example, the lowest validation loss. So you could call this to save your model parameters in order to load into your model later for inference or testing. So for how you would actually load your model is you've saved your model, you've saved the parameters of your model and to a certain directory. So all you would need to do is load that back in and then just call model.loadStateDict. And then yeah, it's pretty simple. So now let's get into coding. So let me switch over here. Okay, so in this task, we're basically going to go through a simple clinical text classification using NLP. So so this will be split into 3 sections, as I mentioned earlier. And the task here is actually determining the medical specialty of a patient note. So we're going to have these notes written by that, and hospital notes are common. They're written by like doctors and nurses and stuff. So I want to see what kind of specialty that is. So the actual, the complete data set for this consists of many different specialties with many multi-class classification tests. But for the purpose of making this demonstration simple, we're only dealing with 2 classes. So there's surgery and cardiovascular. So keep that in mind as we continue. So first, let's start by exploring our data set. So we're just going to import some libraries, which you'll see the NumPy and Pandas is standard. We'll go through why each of these are important as we go throughout. So let's import them. Okay, so next I have this function here that will read in the data frame, and it will, so there are some transcriptions within this data frame that do not have values. So we're going to drop those, reset the index, and then have the data frame. So so let me just upload the actual data. So I have a link to the data also as well at the top.
Vish, are you able to increase the font size?
Is this better?
Yes, thanks.
Okay, so yeah, now we have now we can call this function in order to load in our data frame and remove the transcriptions that do not have values. So let's call let's have our dfb, and then let's just look at how this data frame looks. So we can see that this is the general framework of the data frame. So we can see that there is the medical specialty, which we're going to be treating as our Y value or our label. And then we have the actual transcription. So there are also other factors here that you can imagine would be useful for this task. So for example, there's description, there's keywords, which you could also pass into a model to basically supplement the transcription for your classification. So that's definitely something that you could do for further steps. But for the purpose of this tutorial, we're only going to be dealing with the transcription and the medical specialty. So so I have this function here that will so we have these labels, right? It's surgery and cardiovascular, but I basically wanted to just have an easy way to convert this string, which is surgery, to a number 0 or 1, because we're dealing with binary classification. Obviously, we can't have our model predict the string. Our model is going to predict a number. So all this function is going to do is it's going to get a list, a set of the specialties, so all the unique specialties, and it'll create a dictionary mapping all the specialties to particular numbers. So if we look at the output here, we can see that 0 is surgery, 1 is cardio. So this function is also necessary if you're going to do multi-class classification with more specialties. So this will make it a lot simpler in that regard. So why don't we look at a particular transcription example? So we can look at, let's look at the first transcription. So we can see that qualitatively, so we know that the label for this is surgery, right? And qualitatively, we can see that this seems like a surgical note. So there's mentions of the operating room, there's mentions of like screws and stuff. So as a human reading this text, we can see that this is probably a surgical note. So so keep that in mind. So this is something that we can do so pretty easily. So we would expect this NLP algorithm to also be able to accomplish this task.
Vish, question from the audience. Are you able to share your Colab link so that people can follow along on their own?
Oh yeah, of course. So does that share with everyone?
You could pop it into the chat.
So I sent the full completed one, but I can also send like the ones that has like missing stuff that I'm going to fill in here, if that would also be helpful.
I think this should be good for now.
Okay, sure. So yeah, we have this medical note. So let's continue to build our vocabulary. So this is a critical step. It's a critical step in the process where we basically want to loop through all of our transcriptions and see what unique words we have, and then basically map each of these words to a particular index so that when we're loading in these transcriptions, we can just convert them to a vector of numbers that our model can deal with. So what we're going to use to do this is a tokenizer. So what this tokenizer is going to do, and this is from the Torch text library. So it's basically going to be able to convert this this string, it's going to split it into a list of words. And so basically each index of this list would contain each of these words in the sequence. So this is useful for us because we want to track each individual word. So the unique word. So we need this kind of tokenizer to do that. So let's fill out this function here. So I have this function that builds the vocabulary. So I just want to note that we're going to take in the data frame. We're going to take in this tokenizer, and there's actually this counter object. And all this counter is going to do is it's going to keep track of the unique words that we see. And this we can use with the Torch text vocabulary library. We can pass that in, and we can pretty easily generate our vocabulary dictionary. So with those declared, we're going to take those in, and we're going to return our vocabulary. So let's start here. So first, we're going to get a list of all the transcriptions. So now we can iterate through this list and deal with each transcription individually. So for each transcription within this list of transcriptions, so first, we're going to go through a standard preprocessing technique in NLP where you would engage in lower casing and also removing punctuation. So the reason why we do this is because when the vocabulary is a smaller size, this results in less complex tasks since there's a lower feature space basically. So in doing so, when we make them lower, for example, like there are words here that, for example, the word "the." So whether the word "the" is capital or not capital, it's likely going to mean the same thing in the sentence, right? So there are many cases like this where we actually do not care about the capitalization. And keep in mind that there are cases where you would care about the capitalization. In that case, you would not lowercase it, but lowercasing is very common. And then also for the same reason, we're going to be removing the punctuation. So that's all that this line is going to be doing. It's going to take this string and it's going to convert it to a version that's all lowercase and without punctuation. So next, we're going to call our tokenizer to split the transcription into a list of words. So let's do that right now. So let's call words. And all we need to do with this tokenizer is we need to call it on our string. So our string is denoted by I here. So now we're going to have this list of words. So another thing that we're doing is we're tracking the maximum amount of words present within each of these transcriptions. And this is important because we want to send in the same length vector into our model. But the issue is that each of these transcriptions have different lengths, obviously. So we want to track the max length transcription and then pad all of our transcriptions later on to reach this max length. And there are definitely models right now that can deal with this in other ways. But for the purpose of this demonstration, this is the most palatable way to do it. So what we're going to do is words is going to be a list of the words that we have, right? So we're gonna find the length of that, and if it's greater than what we're currently tracking, we'll just update the maximum length. So that makes sense. So then and then what we're going to do is we're going to update our counters. So instead of like looping through the words, finding all the unique words, we can easily just use this counter that we pass in. We can just pass our list of words into the counter. So if we just do counter.update, and then we pass in words. So all this is going to do now is it's going to update the counter. The counter will keep track of the unique words that we see, as well as the frequency of these words that it sees. And from there, you can just denote a dictionary using this counter. And I should note that you can actually choose the minimum frequency of words in order to build your vocabulary with. So for example, say we didn't want to deal with all the unique words. We only want to deal with words that appear more than 10 times and disregard other words. So we could do that by just changing the minimum frequency to a higher amount. So for this example, I'm going to use a minimum frequency of 1, but you can imagine there are cases where using a higher minimum frequency would be helpful. So next, we're going to set a default index to this vocabulary. So what is this vocab going to do when it sees a word that's not in the dictionary? Because we're going through all of the data that we have right now, but say we want to apply this model in a new case. It sees an unknown word. We need it to return some sort of default index. So we're setting that to 0. And this is also what we're going to be padding our input vectors with. So therefore, this function is going to return the vocabulary and the max length. So let's see what the max length is. And let's see the length of our vocabulary. So it seems like the max length transcription is 1,591 words. And then the length of the vocabulary is 18,395. And both of these seem pretty reasonable. So next, we're going to move on to PyTorch. So this is where we're first going to build our data loader. So first, we're going to import some libraries. So we have torch, then data loader, and then a functional command, which we'll see is used to convert the ground truths into one-hot encoding. So let's import those. Great. So so as I mentioned in the presentation, the data loader will have 3 key components. So you have the initialization, you have the get item, and then you have the length, and then you have like additional helper functions. So let's start the initialization. So what we're going to do is we're going to pass in these following parameters, and you'll see where they're used. So for this initialization, we want a list of the transcriptions that we have. So we can easily get this by just we're passing in the data frame, so we can just find transcription. So this will basically just get us a list of all the transcriptions, and we can do the same thing for the ground truth. Great. So we have that conversion dictionary. This is, as I mentioned, we're going to be loading in these ground truths, right? They're just going to be strings that are saying like what medical specialty we are, but we want to convert that to a number. So we want this conversion dictionary, which will make it easier. Okay, number of classes should be the length of this conversion dictionary. Okay, and then vocab we're passing in, and then max length that we're also passing in. So let's move to the get item function. So the get item function is going to be passed, an index is going to be passed to it. And what this is doing is it'll tell us that, okay, we're at a set index. We want you to return your input and your ground truth for that index. So what we're going to do first is we're going to find the current ground truth and the current text. We're basically going to use this index to index these lists that we just defined earlier. So for example, if we want to get the current text that we're at, we would index self.text with the index that's being provided by the get item function. So we could repeat the same thing with the ground truth. So keep in mind that this ground truth is going to say something like surgery or cardiovascular / pulmonary. And to convert that to a number, we first want to call our conversion dictionary on this. So let's do. So now this is going to be a 0 or a 1. So one thing that we're going to do is actually convert this to one-hot encoding. So this is important if you're doing multi-class classification. It's not strictly necessary for binary classification, but I'm doing it for the purpose of extending this to multi-class classification easily, nevertheless. So all this is going to do is say we have 0. So instead of this being 0, it'll return 0. It'll return 1, 0. Whereas if the ground truth was 1, we would have 0, 1. So basically, like the index of this array is going to be set to whatever the true value, whichever one is correct. So the index of if the ground truth is 0, then the index of 0 will be set to 1. If the ground truth is 1, then the index of 1 will be set to 1. So that's all this does. So this is the functional thing that I imported from PyTorch earlier. That's all that's doing. And yeah, so next, we want to tokenize our text. So keep in mind that when we're indexing our text, we're just getting the string, right? But we need a vector of numbers in order to send into our model. So what we're going to do, let's just imagine that we have some function called process text. So we call that here and pretend that this just outputs our vector of numbers. And obviously, we're going to be writing this function, but imagine it just does that for now. So it's going to send us our vector. So we would pass in our current text, and then we're going to return a dictionary. So this dictionary will just have our input and our ground truth. And you could also just return like a tuple, return like sample, comma, ground truth. But this is useful. This is just useful for keeping yourself organized. So let's return input is the tokenized text, and then ground truth is the current ground truth. So our get item function is complete then. So now all we need to do is actually flesh this process text out. And the steps that we take in this will actually be very simple to the steps used to generate the vocabulary. So let's head down there. So process text. So we're going to be given this input text string, and we want to convert it into a vector of numbers. So first thing that we're going to do is we're going to do the same thing that we did earlier, which is lowercasing the text and removing the punctuation. So we're going to do that. We're going to get text over here. Okay, and then we're going to call the tokenizer like we did before. So remember that we initialize the tokenizer here. So all we need to do now is just call self.tokenizer of our text. So now we're going to have a list of these words. And so instead of doing what we did earlier, having like a counter object, now all we need to do is iterate through this list of words and then convert, using the vocabulary dictionary, convert each of these words to its associated number, and then add that to our vector. So let's do that right now. So for each word in this list of words, we're basically going to append to tokenize. So we'll do tokenize.append, and then we're going to append the, so this is where we call our vocabulary, which was also initialized. So self.vocab of the input word. So now you can imagine that tokenized is some array of numbers. So, but this is not the length of, so keep in mind that we want to send in the same length array to our model, right? So this is why we've been tracking the maximum length. So we want to make sure to pad our input array to that max length. So there are functions that you could do this with, but I find that like Python's just normal list syntax is pretty easy for this specific task. So all we're going to do is we're going to pad zeros with the amount of zeros that we're going to pad is equal to the maximum length minus the current length of the tokenized of our tokenized sequence. So now you can imagine that all of these sequences that we're returning are going to have the same length as the maximum length that we've been keeping track of. So that's the data loader, except one thing left that we need to do is define this length function. So as I mentioned earlier, all this function is going to do is return the length of the input data that we're going through. So yeah, and the length of this will just be equal to the length of the text that we're dealing with. So we can just return the length of self.text. So great, this is our dataset class that's complete. So all we need to do is just run that, and then we're going to be passing this into the Torch data loader in order to get our data loaders. So here's a function that I have here that will basically take in all these parameters that you need to pass in order to declare the dataset class, in addition with some others that are necessary for the data loader, which I'll get into. So all I'm doing here is I'm resampling the data frame. So all this is going to do is shuffle it in case there are some inherent biases with the way that it's ordered. So it's just a good idea to shuffle it before splitting it. So next, I'm going to choose a point based on the train validation ratio that I send in. So say I want an 80% train set, a 20% validation set. So I'm basically going to get some point here that's between 0 and the length of the data frame. And using just normal data frame indexing, I can find a train set that is equal to 80%, and then I can find a validation set equal to 20%. So from there, we have these two different data frames corresponding to the different sets that we have. So let's then declare our data loaders. So first, we'll have our data set, which is the class that we just declared here. So we'll call that with, we'll pass in. So for the train data set, we want to pass in the train set, and everything else is the same. And then you can imagine the same as the val data set. We just pass in the val set, which is this index data frame. So from there, we call the data loader function, the data loader from PyTorch. So as we can see, we pass in this dataset class. And then there are some other parameters here that are worth noting. So firstly, we have shuffle. So what shuffle is going to do is every time this data loader is called, instead of just returning the batches in the same order, it's going to shuffle them each time. And this is important because when you're training a model, if you don't shuffle, then the model can just memorize to output just a sequence of numbers that comes out from the data loader, like that specific order. So that's obviously not what we want. So we would set shuffle to true, especially for training. But for validation, this is not necessary at all, since we're just using that as a point of evaluation. So next we have number of workers, and this basically refers to the amount of CPU threads that the data loader uses. So typically, if you want, data loader will run faster if you use a higher number of workers, but this also places more computational tax on your system. So I think for Google Colab, the max is 2, so that's what I'm using right now. And we have the batch size. So the batch size is actually a very important hyperparameter, and it refers to the amount of each sample that is outputted by your data loader each time you iterate through it. So for example, if I have a batch size of 20, which what I'm using right now, every time for every time I go through my data loader, for every step, it's going to return 20, a set of 20 inputs and 20 ground truths all stacked together, which our model can process in parallel. And then finally, there's this argument called pin memory. So this is something in PyTorch where if you know that after receiving data from the data loader that you're going to move it to a GPU, it just makes the process more efficient. So that's what all of this does. So we're basically just going to call this function, and it's going to return to us the train data loader and the val data loader. And keep in mind that I'm using a train validation split of 80%. I'm passing in the vocabulary that I've generated before, passing in the max length, which we need for our data set. And then we're choosing number of workers of 2 and a batch size of 20. So before we get into the model and training, let's just do a sanity check to see whether I did the data loader right. So let's just loop through one batch of the data loader and just look at the output. So if we look at for iData and enumerate. So let's just print out, as we can see, the data loader is going to return this sample that is a dictionary corresponding to the input and the ground truth. So let's just print out and we'll print out the ground truth. And then we'll break since we only want to see one of these. So this is what this is just an idea of what our input and ground truth is, right? So we're going to have our input be basically, you keep in mind that our batch size is 20, right? So this is a stack of 20 different inputs and 20 different ground truths. So let's look at the first input. So this is a vector of numbers, which as we defined earlier is just from our sequence of words. Each word is translated to a number, and there we can see that there are zeros that are padded to the end. And this is what we expected, since we padded each of these arrays in order to reach the maximum length that we're setting to this model. So that makes sense for the input. And then we have the one-hot encoding for the ground truth. So we can see that this is a cardio patient or a cardio node because it has a value of 1 in the 1 index. So this is just a representation of what the one-hot encoding is. So great, this tells us that our data loader is likely working. So we can proceed to our next step, which is defining the model and training. So we're gonna import some more libraries from PyTorch, which are necessary to define our model and optimizers. So let's do that. So this is just a super simple NLP classifier module that I found in the PyTorch tutorial. So all it does is it generates embeddings based on the vector that you send in, and then uses fully connected layers to generate your classification output. So we'll just run that. So next, let's get to defining the model. So the parameters that this model takes in is the length of your vocabulary, which is and then the embedding dimension, where it's basically going to embed each part of the sequence into a length of 300 here. And then we're going to have number of classes, which basically correspond to the number of basically how the size of the output of the model from the fully connected layer. So from there, we're going to use the loss function of cross entropy loss. So we're using cross entropy because this is very common for classification loss. So it's sort of standard in that regard. And then we're going to use the optimizer of Atom with a learning rate that's set to whatever learning rate that we choose. So in this case, we're just choosing this learning rate. So one thing that we should do is transfer our model and criterion to the GPU if it's available. So as I mentioned, one of the key advantages of PyTorch is being able to transfer your model to a GPU if it's available, and this helps speed up training by a lot. So what we're going to do is we're going to say if torch.cuda is available. So if the GPU is available, then we'll send our model and our loss function to the GPU. I spelled that wrong. Right. So now, if the GPU is available, we'll be sending our model and criterion there. So now this function is just going to return the model, the criterion, and the optimizer that we're using. So we can go ahead and just run this. Great. So now we finally reached our entire training loop. So yeah, let's start working through it. So we first have this function that that basically we want to be tracking our accuracy of the model for each batch. So you can imagine that for each batch of 20, we're going to have a set of ground truths and we're going to have a set of predictions the same shape as the ground truth. So we basically want to see like how much of this 20 are we actually correct on. So that's what this model is going to do. So we can see that this function is going to do. So we can see that it takes in two parameters. So there's output and the ground truth. So the first thing that is important to note is when you're dealing with if you want to deal with these tensors in NumPy, because the output of the model is going to be a tensor, same as the ground truth. When you're loading them in from the data loader, they're actually tensors. So like if we go back here, these are tensors. These are not NumPy arrays. So the PyTorch data loader actually converts it to that directly. But if we want to deal with them using NumPy commands, like for example, numpy.argmax, we do need to convert it back to NumPy. And it's important that you need to detach it from the GPU when you're converting to NumPy, because NumPy does not work on the GPU. So we would convert our output and our ground truth back to NumPy. So we would do output equals output.cpu.detach.numpy. So this is basically going to allow our output to, this is going to make our output in NumPy array, basically. So we can do the same for our ground truth. Great. So now we're going to have these NumPy arrays. All we're going to do is we're going to loop through the output and we're going to see if the argmax of the output, so keep in mind that this is the one-hot encoding. So basically, if the index, find whatever index has a higher probability associated with it that's predicted by the model, and if that's equivalent to the ground truth with the argmax of the ground truth, then we'll add a count. We'll add to the count correct, which we're tracking. So basically tell us like for any batch that we send in, how many do we have correct, and this will be necessary for calculating our accuracy. So next, let's enter our training loop. So here are some lists that I just declared at the top. And the reason why I do this is because we want to be tracking our losses and our accuracy across epochs, meaning that we do need to declare these empty arrays outside of the start of our training loop. So we just declare them here. And then within the actual epoch per batch, we also want to calculate these metrics so that at the end of each epoch, we can find basically the average of these losses across the epoch, and then append that to our global losses. So we're gonna have we've already defined our model earlier, and one thing that's important when you're training is you want to set your model into train mode before you're starting your training process. Now, the reason why this is important is because there are some layers in different models that behave differently in training and validation. So and training and evaluation. So you can imagine, for example, if you're familiar with dropout layers, that dropout layers should behave differently during training and evaluation. So due to that, we're going to be setting our model into train before actually going to the train portion of our loop. So we're going to, so for the purpose of calculating accuracy, I'm basically tracking the amount of train samples that we're dealing with, as well as the amount that are actually correct. So you can see that just dividing both at the end should give us the accuracy. So first, let's loop through the train data loader. So this is going to be the same process that I did as my sanity check earlier. So I just do for I data in enumerate train data loader. And I should specify that this specific line, all it's doing is we're getting the data from each iteration of the data loader, but we're also getting an index. So the index we're not going to use, but it's helpful if you want to track the indexes across each batch. So for example, what is the total number of steps that your data loader takes? So for that kind of stuff, you would use this index term. So first thing we're going to do is we're going to get our data out of this little dictionary that we have that we know our model returns. It returns a dictionary of the input and the ground truth, right? So from this, we're going to get our data, and then we're going to move it to the GPU if it's available. So let's do, so the input to our model is equivalent to the data that we're getting input. So if we go back up to the data loader, you can see that we return an input and ground truth dictionary. So yeah, and then we can have the ground truth. And then this is just something that I found through bug testing, but the ground truth for the calculation of the loss does need to be in the double form. So I'll just convert it there. Now we're gonna do the same thing that we did for the model, right? So we moved our model to the GPU by first checking if the GPU was available and then moving our data there accordingly. So we're gonna say if torch dot So if the GPU is available, then let's move our input to the GPU and let's move our ground truth to the GPU. And so I should note that if your model is on the GPU, then your input and your ground truth will both need to be on the GPU, or else you won't be able to calculate, for example, the loss if they're on different devices. So, or the model will not be able to process your input if your model is on the GPU and your input is not. So this step is important in that regard. So now all we need to do is call our model to generate the output. So well, all we need to do in this case is call model parentheses input. And this is a case because if we go back to our model, right, the model has a forward function. So when you're calling your model like this, just model parentheses, whatever your input is, you're going to call the forward function. And the forward function, as we can see, it's going to take the text, it's going to generate the embeddings, and then just pass that into the fully connected layer. So that's a rationale for just calling model in parentheses input, and this is going to give us our output. So our predicted output, and then we're going to calculate the loss between this output and the ground truth. So we defined our criterion earlier as cross entropy loss. So the parameters that this takes will be the output of our function, and then the actual ground truth. So we're going to have this loss here. And now what we need to do is we need to update our model. So the first thing that we're going to do is we're going to reset the gradients on our optimizer. So this is important because every time we calculate outputs from our models, the gradients are calculated, right? And when we're calculating new outputs, we don't want these gradients to be just simply added to the prior gradients. We want to reset the gradients and then use our loss to update these gradients and then update our model accordingly. So we're going to reset the gradients on our optimizer. We're going to then backpropagate our loss. So let's take our batch loss. And the reason why I'm calling this batch loss is because this is a loss across all the images within the batch. So we're actually updating our model. In this case, there's a batch of the 20, right? So we're updating our model basically every 20 images. So we'll call backward. This is as I mentioned in the slides, this is just the basic process to backpropagate the loss. And then we're going to step. So this will basically update our model parameters. Great, so this should update our model, calculate our loss, update our model, and the last thing that we need to do is basically just keep track of these metrics. So we have our loss, so we'll add that to our epoch losses. So this is losses within the epoch. So we can then average that list in order to find the global losses for the epoch. Then we have the count of we're adding to our count of the amount of samples that we're dealing with, and then using this function that we defined at the top here, as I mentioned earlier, we'll find how many of those we actually got correct. So you can imagine at the end, we're just going to divide train count correct by train count to find our train accuracy. So yeah, now that's the train part of it that's over with. And usually when you're training a model, you're going to be doing your training with validation. So basically, you'll go through your train, you'll go through one iteration of your entire train set, and then we'll transition to validation mode, where we'll evaluate the performance of the current model on a validation set, and then typically you would save the best model based on the best validation score, and then apply that model in the future. So one thing that we need to do is, if you recall, we did model.train over here, and that sets our model into train mode, because as I mentioned earlier, there are layers that behave differently in different modes than we want them to. So in that same vein, we need to transition it back to validation mode. So we just need to do model.eval. So that should reset all those layers. And then another thing is that when we're applying our model in validation, we do not want to be accumulating the gradients, because firstly, this takes up unnecessary memory, because we're not going to be because we're not going to be actually using the gradients to update the model. So it's just not necessary for us, and it'll slow down your actual implementation. So we would do with torch.nograd. So all this does is it says no gradient calculation within this declaration. So next, it's going to be basically the same exact thing as a train loop, except we're not going to be updating our model. So we can see that we have this validation count and validation count correct. So that's just to keep track of our validation accuracy. So next, let's loop through the validation data loader. And this is going to be the same thing that we did earlier for the train data loader. So for I data in enumerate val data loader. So we're looping through the val data loader, and same thing as earlier, we're going to be moving our data to the GPU if the GPU is available. So first, let's actually get our input and ground truth from the dictionary that we're getting from our data loader. So and then once we have that, we're going to make sure that we have access to the GPU. So if torch.CUDA is available. Okay, so now they're on the GPU if the GPU is available. So we're going to find our output using the model same way as I did earlier. So model parentheses input. And then batch loss, we're going to calculate the same way. So criterion of the output versus the input, versus the ground truth. So now we're not going to be updating our model. Instead, we're just going to go directly to tracking the metrics. So we're going to track our losses, and we're going to track the count correct and the count that's not, and the total count. So we can see that at the end of each epoch, what we're going to do is calculate the average loss. So we're going to take the length of this list of losses, and then we're going to divide the sum of the losses by this length. So basically, all these lines are doing, these two lines, they're taking the average loss over the entire epoch. So next, we're going to find the train accuracy, which, as I said earlier, we're just dividing the count correct by the total count. So we would do that same for validation. And then all we're going to do is, for each epoch, we're going to be tracking our metrics via the command line. So all this means is that we're just going to be printing the epoch number. So in our entire epoch loop, recall that we're iterating by epoch. So track the epoch number, track the epoch loss, the train accuracy, the validation loss, and the validation accuracy. So you can imagine that when I run this, we're going to get like 20 such lines where corresponding to each epoch. And hopefully this will allow us to monitor whether the loss decreases over time. Well, specifically the train loss decreases over time and the train accuracy goes up over time. So that's what we want to see. And then the val loss should also decrease depending on the task, and then the val accuracy should increase depending on the task. So assuming that I did not make any mistakes here, if I run this, then we should just start getting that output. Oops. So okay, yeah. So as I mentioned earlier, the ground truth does need to be in double. So great. So it seems to be working. And one thing that we can see is that the train loss is decreasing over time with epochs, and the train accuracy is going up. So this is what we would expect with such a model. One thing to note is that the validation loss is a lot more variable, and this makes sense since this task isn't very difficult. So we wouldn't expect it to take that many epochs for it to do well on the validation set, given how well it's already doing on the train set. So, but we can see that it achieves an accuracy of like 87.5%. That seems to be the highest around epoch number 9. So yeah, the model basically appears to be working as expected, but there are numerous ways to improve this performance. So as I mentioned earlier, firstly, you can use a different model. So right now we're just using a very simple NLP model. So you could definitely use a simpler model in that regard. And then also there are things with the data set. So if we go back to the data set itself, as I mentioned earlier, there are these keywords and descriptions. So many of these things that you could use to augment into your data pre-processing pipeline in order to have more potential delineating features between the output and the ground truth. So those are sorts of things that you could play around with. And then, yeah, so you could experiment with a bunch of that, but that's the entire gist of using PyTorch for NLP. I would recommend all of you to try this with the entire data set. So this involves, I think, around like 22 different specialty classes. So it's a more difficult classification task. I'm not sure whether this model would work well on it. I haven't tried it myself, but it's definitely something that you should try. But other than that, that's it.
Wonderful. Thanks a lot, Vish, for the very nice presentation and overview of a very popular tool that's getting increasingly important. So thank you.